Let's analyze some circuits, all right? So starting from the beginning, not the end. Circuit analysis with resistance. Here's an example. So we have a circuit here with 3 resistors. This is a combination series parallel circuit. It's not fully series or fully parallel. These 2 resistors, R2 and R3, are in parallel with each other, but they are in series, so they're sort of combined in series with R1. The resistance values for each resistor are given, as well as the voltage on the battery, which is pretty typical because, when you build a circuit, generally you know the voltage of the battery that you're using because you're the one making that decision, and you know the resistance values for the resistors because, once again, you're choosing the resistors. So it's very common to have this particular information known to you already when you start to analyze a circuit, when you're actually building it. So basically we have to find everything else. We have to find all the currents, most of the voltages, and also the total resistance. Here's a sort of a better diagram of the circuit, and I'll shrink this down so we can do some work on the side. Now I would really strongly encourage you to keep track of your work in a table. You're always finding voltage, current, and resistance, and you're always doing it for a whole bunch of components, so it just makes everything way easier if you keep track of everything in an organized way. Okay, so now analyzing circuits, look, there are an infinite number of configurations of circuits that you can build, and there's no single step-by-step process that will always solve a circuit. Like, you shouldn't always find VS first or IS or whatever. Like, there's no order to it. You have to kind of just examine what you have, and you have to choose from among the various methods that you've learned based on the information that you have. So, what are the methods that we know? So we know Ohm's law, which is voltage equals resistance times current. We know how current and voltage work in series and parallel circuits. So current is constant across a series circuit, and it adds up in parallel circuits. And then voltage is vice versa. And then we also have these laws about resistance. So resistance adds up in a series circuit, and it adds the reciprocals in parallel circuits. So those are kind of the tools we have at our disposal in order to solve and analyze a circuit. So looking at this one, the thing that jumps out at me first is that we know all of the components of resistance, but not the total resistance. So we should be able to use resistance laws to find this R total, also known as RE for R equivalent, the equivalent resistance. Now it's going to take a couple steps, because first of all, we're going to find the equivalent resistance of these 2 parallel branches, which involves the reciprocal formula. So add up these 2 fractions, which comes out to that fraction, flip it around, and then let's turn it into a decimal, because who wants to work with these annoying fractions? So the equivalent resistance of these 2 parallel branches is 14.6 ohms. Now these 2 are in series with this one over here, and in series you just add the resistances. So the total resistance of the circuit is 29.6 ohms, and I'm going to fill that into the table. Okay, so take a minute before I say anything, pause, and just think about, given that new piece of information, what else can we find? And the answer is you can use Ohm's law, because if you look at the source, well, we know the voltage already, and now we know the resistance. And so because we know 2 of those quantities, we can find the third one using Ohm's law. So in this case, Ohm's law can be written as current is equal to voltage divided by resistance. So plug in those numbers and you get 0.4 amps. Okay, so once you know the current at the battery, well, just think about the current as it goes around the circuit. Well, it's still in the same path. And so the current here at the first resistor is going to be exactly the same because it's in series with the battery. And you can imagine we're filling in the chart as we go along. I'll do it basically at the end of each slide because it's less annoying that way on Google Slides. So once we know the current at resistor number 1, we already know the resistance there. So once again, you can use Ohm's law to find the voltage because we know 2 out of the 3 quantities. So voltage is equal to resistance times current, and you get 6.1 volts. Okay, let's update the table. So here's what we know now. So we know everything about the source and everything about resistor number 1. So now we have to solve the other 2 resistors. Okay, so let's think about voltage here for a second. You can't solve current because current splits and you don't exactly know how much it splits. You can't say that it splits in half. In fact, it definitely doesn't because these resistors are different. But voltage, remember that basically electrons have a certain amount of voltage and they kind of deposit it at different places along the circuit. So electrons come out of the battery with 12 volts. And we know that every electron passes through resistor number 1 and drops off 6.1 volts. So how much do they have left? Well, you just subtract. So each electron coming out of resistor 1 has 5.9 volts left to drop off. And remember that it's going to deposit all of its volts by the time it gets back to the battery and refills its volts. So no matter which path the electrons take, they are going to drop off 5.9 volts at the resistor. And so the voltage V2 and V3 are both equal to 5.9 volts. And so once you know that, you know everything except those two currents, and you can use Ohm's law to find the last two currents by doing voltage divided by resistance. And I didn't show that work, but those are the answers, 0.24 and 0.17. Okay, example number 2. So take a moment and look at this circuit. It's only a little bit more complicated than it's almost identical to the previous circuit, to be totally honest with you, except for the numbers. The only difference is that there's an extra resistor on this parallel branch up here. And so that introduces another layer of this kind of like series versus parallel complexity, because you have these two in series with each other, which are in parallel with this one, which the whole thing is in series with this one. And you could do this infinitely. You can make it infinitely complicated if you wanted to. I don't know why you would want to. That would be insane, unless you want to get into theoretical electronics, which is a real field of study and is kind of cool if you're a nerd like me. Okay, so this is what's now. Okay, so let me back up. The real difference in this question is what is given. You're given a very different set of information than the last time. You don't know the resistances, but you know a bunch of voltages and you know a current. And you know one of the resistances. So here's what you know. Oops, that's the last question. Here's what you know. I filled in the chart. We don't know anything about resistor number 2, but we know 2 things about resistor number 3. So that's actually a nice place to start. Oh, that's not where I started. So actually, okay, here's what we're going to do. I personally like starting with current. I just find current is like, for me, the easiest to wrap my head around. I just seem to understand it a little bit better than the other two. So immediately when I see that the current here at resistor number 1 is known, well, it has to be the same as the current at the source because they're in series. So I immediately fill in the current at the source is 0.5 amps. Okay, so then if we think about parallel circuits, we think about the voltage in parallel circuits. So remember that, okay, so electrons come out of this battery with 12 volts. They drop off some volts here. We don't know how many, although you could probably figure it out. Anyway, the point is we already know that the voltage at resistor number 4 is 5 volts. So some electrons come this way and drop off 5 volts. Well, other electrons are going to go the other way. And so they're going to also have to drop off 5 volts on their path. Now the difference is their path has 2 resistors on it. This one has the voltage of 2.5 volts, which is known. And so if an electron is going to debit 5 volts total along this path, and this one's 2.5, then this one has to also be 2.5 to add up to 5. So V2 is equal to 2.5 volts. And then finally, Ohm's law, this could have been done from the beginning, but when you have a component where you know 2 parts, two of the numbers, 2 of the values, you can always find the third. And so there is, oops, I put the wrong unit here, but the current at resistor number 3 is 0.25 amps. Okay, let's pause there to update the chart. There are the filled in numbers. Okay. So that last part that I just solved, 0.25 amps right here. Well, this resistor is in series with this resistor, so they have to have the same current. So that current there is 0.25 amps. Did I say 0.25? Oh, did I make another mistake? Oh, geez, guys, it's late at night. Okay, 0.25. Oh, it's wrong on the chart too. Okay. Blah, 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 blah. Wow, I am going insane. Okay. Next, in series, you can think about the fact that, well, electrons come out of the battery with 12 volts. For the ones that take this bottom path, we know they lose 5 volts here. And we know that in total, they have to lose 12 volts because that's how it works. So how many volts do they lose here? Must be 7. It must add up with this one. So basically, you can say V1 plus V4 must equal Vs, V of the source. So V1 is 7 volts. And finally, well, not quite finally, but finally for this slide anyway, let's look at the current up in this parallel branch. So the current at resistor number 4 is not known, but the current up here is known. So the current up here is 0.25 amps, right? And we also know that the current in the sort of main part of the circuit is 0.5 amps. And so how does it split up? Well, if you have 0.5 and 0.25 goes this way, how much goes this way? It has to also be 0.25 to add up to 0.5. And I'm assuming I made a mistake on that, which I will now fix. That should be 0.25, not 0.2. And go to the next slide. I'm going to fix these on the chart. And so then finally, if we just take a look at the chart here, we know all the voltages and all the currents. So for resistance, you can just use Ohm's law a bunch of times. And as a matter of fact, in this whole question, we didn't have to use resistance laws at all. But if you get to the end of the question, you could actually use them as a sort of check method. Whenever you're doing a question, if there's two ways of solving something, it's a really good idea to use one way to actually solve it, but then use the second way as a way of sort of independently checking if your answer is right. If you get the same answer both ways, then you're like pretty 99.9% sure that you got it right. I think I need to fix a couple of these because of that mistake I had just made. So R4 should actually be 20. And I think that's it. Okay. So in summary, these are a couple of strategies that you can use in order to do successful circuit analysis. So if you're given all the resistances to start, use the laws of resistance to find the total resistance. And as I mentioned, this is a common set of information to know because it's realistic, because that's actually how you build circuits. You can also look for voltage laws for series and parallel circuits, as well as current laws. I don't know why I didn't say current, but look for voltage and or current laws for both series and parallel circuits. And finally, look for Ohm's law. So basically, anytime you know two values of a particular component, you can always find the third using Ohm's law. And those are some strategies and some examples for doing circuit analysis.